mechanism is like this. This angle is theta, and this link is input link. It's rotating with a uniform angular velocity of 3 radian per second. Okay. So now I think you got the direction of rotation. Direction of rotation. Dimensions of the mechanism are given like this. This is 20 units. And this is some 20 centimeter. This is some 40 centimeter. 40 centimeter. 50 centimeter. And this is also 40 centimeter. Those are the dimensions of the mechanism. This is 50. He gave angular velocity of link number input link, and he is asking us to find out angular velocity of the coupler and angular velocity of the output link. Angular velocity of the coupler and angular velocity of the output link. Just listen here. So I will discuss this problem and you solve the other problems. So they're asking us to do velocity analysis when theta is 180 degrees. Okay. So velocity analysis is always done at an instant. Okay. Velocity analysis is always done at an instant because, so we have seen the formula for angular velocity ratio theorem. So it depends upon the distances between the eye centers, okay? So distance between I1m and IMN. If you see the formula, it is omega m into, so it's omega m into distance between I1m and IMN. So is same as omega n into the distance between I1n and IMN. This formula is easy to remember, okay? If it is omega m, it should be 1m. So Mn will be present in both the cases. If it is omega n, it should be 1n. Omega n, 1n. So this is Mn, Mn will be both the cases. Okay. So if you want to solve the problem, you need to know the distance between these eye centers. Okay. You need to know the distance between these eye centers, and the location of these eye centers is not fixed. The location of these eye centers will be different for different configurations. Okay. So when this angle is 0, so the eye centers locations will be different. When this angle is 180 degrees, the eye centers will be different. When this is some other angle 45 degrees, the location of eye centers will be different. So for different instance, the location of eye centers will be different, okay? Location of eye centers will be different. So velocity analysis is always done at an instant. So for different instances, these distances are different. So for different instance, angular velocities of different links will also be different. They will not be the same all the time. But the question is, he told that velocity of this link is uniform. So it is remaining same all the time. But other velocities will be changing, okay? At different instances, they will be different. So depending upon the location of eye centers. Okay? So he is asking us to do velocity analysis at an instant when this theta is 180 degrees. So the first step is you have to draw the mechanism when theta is 180 degrees. When theta is 180 degrees, how the mechanism looks. So when theta is 180 degrees, the mechanism looks like this. This is fixed link. So if I say theta is 180 degrees, this link will come here. And this is like this. And this is like this. So this is link number 1. So this is link number 2. This is link number 3. And this is link number 4. These are 4 links. Try to look at the eye centers. So 1 and 2 are connected by a turning pair here. So 2 and 3 are connected by a turning pair here. 3 and 4 are connected by a turning pair here. I34 lies here. 1 and 4 are connected by a turning pair here. I14 lies here. So I want to look at the remaining instantaneous centers. You draw a polygon having number of sides equals to number of links. So there are 4 links. I am drawing a polygon with 4 sides. Try to look at the remaining eye centers. So I want to look at I13. See how can I go from 1 to 3? So 1 to 3, 1 to 2 and 2 to 3. So 1, 3, 2, 3, 1, 4, 4, 3, 1, 4, 4, 3. Draw a line passing through 1, 2 and 2, 3. This is 1, 2, this is 2, 3. Draw a line passing through 1, 2 and 2, 3. Draw a line passing through 1, 2 and 2, 3. I'm drawing a line passing through 1, 2 and 2, 3. This line is passing through 1, 2 and 2, 3. Similarly, draw a line passing through 1, 4 and 3, 4. This is 1, 4, this is 3, 4. draw a line passing through 1, 4 and 3, 4. Wherever these two lines intersect, so there I13 will lie. I13 will lie here. I13 will lie here. Similarly, try to locate I24. Try to locate I24. I24. How can I go from 2 to 4? 2 to 3 and 3 to 4. 2, 3, 3, 4. And 1, 2, 1, 4. So 1, 4 and 1, 2. Draw a line passing through 2, 3 and 3, 4. This is 2, 3 and this is 3, 4. Draw a line passing through 2, 3 and 3, 4. So I am drawing a line passing through 2, 3 and 3, 4. This line is passing through 2, 3 and 3, 4. Similarly, draw a line passing through 1, 2 and 1, 4. This is 1, 4 and this is 1, 2. So draw a line passing through 1, 4 and 1, 2. Wherever the two blue color lines intersect, that gives you the location of I24. I24. You know length of different links? Length of different links I am writing like this. Length of this link is 40 centimeter. Length of this link is 20 centimeter. Length of this link is 40 centimeter. Length of this link is 50 centimeter. You do velocity analysis of it. Link 2 is rotating counterclockwise. Okay? It's rotating like this. Velocity is 3 radian per second. Velocity is 3 radian per second. In the question, omega 2 is given in the question. So omega 2 is given as 3 radian per second counterclockwise. So we want to find out first, let's find out the coupler velocity, omega 3. Omega 2 is given in the question. We want to find out omega 3. So angular velocity ratio theorem, the generalized angular velocity ratio theorem, it is omega m, distance between I1m, mn, is same as omega n, distance between I1n and IMM. I1m and I1n. So I am assuming one is 2 and one is 3. So this is omega 2. It's omega 2, distance between I12 to 3. Same as omega 3. This is omega 3. It should be I13 and the common I center I23. Omega 2 is already known. So this is 3 radian per second. Now what is the distance between I12 and I23? So this is I12, I23 is this. The distance between these two I centers is 20 centimeter. Omega 3. Omega 3 is not known. We need to find out omega 3. Distance between 1, 3 and 2, 3. Where is 1, 3? 1, 3 is here. I13. This is I23. The total distance is 60 centimeter. So omega 3 I can say is 1 radian per second. Omega 3 is 1 radian per second. Clockwise or counterclockwise? Omega 3 is 1 radian per second. It's okay. It's clockwise or counterclockwise? Counterclockwise. So how to determine this? So for 2 and 3, you see the location of I12. You see the location of I13 with respect to the common I center I23. Where is I23? This is I23. I12 is lying here. I13 is lying here. So both are lying on the same side of common I center. So both links 2 and 3 will rotate in the same direction. 2 was rotating counterclockwise. 3 also rotates counterclockwise. So at this instant, 2 is rotating counterclockwise and 3 also rotates counterclockwise. Okay. So try to find out angular velocity of link for output link. So angular velocity of output link. So omega 2 is given in the question. Omega 2 is given as 3 radian per second. So we want to find out omega 4. I am writing angular velocity ratio theorem. So omega 2 into distance between I1 to common I center is 2, 4. So omega 4 into distance between, if it is omega 4, it should be I14, the common I center is I24. Omega 2 is given in the question. The distance between 1, 2 and 2, 4. So 1, 2 is here. 1, 2 is here. Where is 2, 4? 2, 4 is here. The distance between 1, 2 and 2, 4 is 20 centimeter. This is 20 centimeter. Omega 4 we need to find out. Distance between 1, 4 and 2, 4. 1, 4 is here and 2, 4 is here. The distance between these two is 60 centimeter. So omega 4 is also 1 radian per second at this instant. Omega 4 is also 1 radian per second. And if you try to see the direction, the common I center is I24. So where is I12 is here, I12 is here, I14 is here. So both are rotating in the same direction. Okay. So for direction of rotation, you have to see the common eye center. Okay, where is the common eye center? Once you look at the common eye center, where is I12? Where is I14? Okay, so I12 is here, I14 is here. Both the eye centers are lying on the same side of common eye center. Both links will rotate in the same direction. Just try to answer these questions. What's the answer for this? So what's the number of eye centers for an 8-link mechanism? So if there are n links in a mechanism, number of eye centers possible are NC2, okay. 8C2. It's 28 eye centers, okay. So what's the answer for this question? So here there are 6 links, okay. Number of eye centers possible are 6C2. 15 eye centers are possible. What's the answer for this question? We have already solved this question. It's not required. Try to answer this question. Phi is the angle between link 1 and link 2, okay? Phi is the angle between link 1 and link 2. Which link is 6th link? This is link number 1, link number 2, 3, 4, 5. Basically that's a slider, okay? Understand, it's a slider, okay? It's a slider. Try to answer this question. When phi is 180 degrees, velocity of link 2 is 5 radian per second counterclockwise, then angular velocity of link 3 is. So phi is the angle between fixed link and link 2, okay? It's a very similar question. So distances, just take down the distances. There's some data missing in the question. This angle is phi. This distance is some 2A units and this is some A units. This is link number 1. This is link number 2, this is link number 3, and this is link number 4. Okay, so he's asking us to do when this angle phi is 180 degrees. So first you draw the configuration when phi is 180 degrees. So when phi is 180 degrees, the mechanism looks like this. Mechanism looks like this. Okay. So you get angular velocity of link number 2. Angular velocity of link 2 is given. Omega 2 is given in the question. Omega 2 is given as 5 radian per second. So angular velocity of link 2 is 5 radian per second. He is asking us to find out angular velocity of link. Find angular velocity of link 3. He is asking us to find out angular velocity of link 3. Omega 2 is given. Omega 3 is asking us to find out. This is link number 1, link number 2, link number 3, link number 4. So I12 lies here. So I23 lies here. I34 lies here. I14 lies here. Okay. So to solve this problem, so you need to look at I12, you need to look at I13, you need to look at I23. Okay. So 1, 2 is located, 2, 3 is located, 1, 3 is not located. Try to look at I13. Now how to look at I13? So draw a polygon having number of sides equals to number of links. So I want to look at I13. So to go from 1 to 3, so we can go from 1 to 2 and 2 to 3. So draw a line passing through 1, 2 and 2, 3. So this is 1, 2, this is 2, 3. So I'm drawing a line passing through 1, 2 and 2, 3. Similarly, draw a line passing through 1, 4 and 3, 4. This is 1, 4, this is 3, 4. Draw a line passing through 1, 4 and 3, 4. Where are these two lines meet? So that is your I13. This is the location of I13. This is the location of I13. So once you know the location of I13, we can write angular velocity ratio theorem. It's omega 2. If it is omega 2, it should be I12. And for 2 and 3, it's I23. The common I center is I23. Omega 3, so distance between I13 and the common I center. So we know this distance, this is 2a units and this is a units. Omega 2 is given in the question, this is given as 5 radian per second. 5 radian per second. Distance between 1, 2 and 2, 3. 1, 2 and 2, 3 distance is a units. So omega 3 into distance between 1, 3 and 2, 3. 1, 3 is here, 2, 3 is here. This total distance is 3a units. 3a units. Omega 3 is 5 by 3 radian per second. 5 by 3 radian per second. It's 5 by 3 radian per second. So direction, if you see, it's given as counterclockwise, okay? Link 2 is rotating counterclockwise. What will be the direction of link 3? So this is the I23. I12 is here, I13 is here. Both are on same side of common I center. So both links will rotate in same direction. 2 is counterclockwise, so 3 will also be counterclockwise. Try to answer this question. So find relative velocity of 2 with respect to 3. He's asking us to find out the relative velocity between two links, okay? And the numbering of links is as generally we follow, okay? 1, 2, 3, 4. So one is fixed link and the count starts and it goes in clockwise direction. So like this, link 1, link 2, link 3, link 4, the same notation. He's asking us to find out the relative velocity between these two links. Whenever I say relative velocity of link 2 with respect to link 3, so it's the relative velocity in the sense angular velocity, okay? Not linear velocity. If I say linear velocity, so different points on this link 2 will have different velocities, okay? Different point on link 3 will also have different velocities. The linear velocities of different points will be different, okay? So the angular velocity for a link will be same, okay? Link will have only one angular velocity. But linear velocities will be different. Linear velocities is r times omega, right? Different points will have different radius for different velocities. Find relative velocity of link 2 with respect to link 3. So he's asking us to find out the relative velocity between two links. Relative velocity of 2 with respect to 3. It means that so what is velocity of link 2 with respect to link 3? If you stand on link 3 and if you observe link 2, what will be the velocity of link 2? That is the question, okay? If you stand on 3 and if you observe 2, what will be the velocity of link 3? So in this case, whenever you find out the relative velocities, so it's required to know the direction of rotation, okay? If both the links are rotating in the same direction, so I say relative velocity is omega 1 minus omega 2. If both are rotating in opposite direction, so then relative velocity will be, so it will be omega 1 plus omega 2 because the direction is different, okay? So we follow a sign convention for finding out relative velocities, okay? So he gave omega 2 is clockwise. So I am assuming clockwise is positive. So omega 2 is plus 5 radian per second. Omega 2 is plus 5 radian per second. And if you see omega 3 is, it's just given, only the magnitude is given, but direction is not given in the question. Direction is not given in the question. First you have to find out the direction of rotation of 3. You know omega 2, you can find out omega 3 by locating the eye centers. So I'm locating the eye centers. When I look at the eye centers, so this is fixed link, link number 1. This is 2, this is 3, and this is 4. This is I12, this is I23, This is I34 and this is I14. This is I14. So if you know velocity of link 2, if you want to find out velocity of link 3, we need to look at I12. So I13 and the common I center. Velocity of link 3 is not known to us, okay? We know only magnitude, we don't know it completely. So when I say velocity, it should be both magnitude and direction, okay? So try to locate I13. So I12 is already located, I23 is located, I13 is not located. So if you extend these lines, so wherever these lines intersect, so this is the location of I13. Now you know the location of I13. So this is the common I center I23. I13 and I12 are lying on either sides of common I center, okay? Since both of them are lying on either sides of common I center, both will rotate in opposite direction. Link 2 is rotating clockwise, link 3 will rotate counterclockwise. Link 3 will rotate counterclockwise. So velocity of 2 with respect to 3 is, what is velocity of 2? Velocity of 2 is plus 5 radian per second, minus velocity of 3 is minus 14 radian per second. So this is 19 radian per second. Get a positive sign, okay? Velocity of 2 with respect to 3. It means that when you stand on link number 3, and if you look at link number 2, you feel link number 2 is rotating 19 radian per second clockwise. Okay. When you stand on link 3, and if you observe link 2 at that instant, you feel 2 is rotating with 19 radian per second, and it's a clockwise rotation. Okay. With respect to 3, 2 will be rotating clockwise. Okay, whenever you want to find out relative velocities, you need to take the directions. Directions are important again. This question is very similar to the previous question today. So nothing is there. Basically, when you want to find out relative velocities, you should know the direction, okay? If both the bodies are moving in the same direction, relative velocity we say v1 minus v2. If both are moving in opposite directions, we say relative velocities v1 plus v2. Why the plus sign is coming? Because the directions are different, so the velocity vectors will have different signs. So when you take the difference, it comes out to be an addition, okay? Here also the same thing. So you basically, you know the direction of this, you don't know the direction of this. You don't know the direction of this one. So if you don't know the magnitude and direction for this one, we use a formula. By using that formula, we get the magnitude. So let's assume I got the magnitude. But how to get the direction? So direction, we have to see the eye centers. This is the common eye center, and where are the other eye centers lying? So here both the eye centers are lying on either sides of common eye center. So now I got the direction also. They rotate in opposite direction. So basically you have to get the direction, okay? By using the formula, we get the magnitude, but here not required to use any formula. Here directly give the magnitude. Solve this problem. What's the answer for this? It's 4. Do velocity analysis when angle O2 is 180 degrees, okay? When O2 is 180 degrees, our mechanism looks like this. I'm calling this is link 1, this is link 2, this is link 3, this is link 4. So I12 will lie here, so I23 will lie here, so I34 will lie here, so I14 will lie here. In the question, he is saying that the input link O2P of a 4-bar linkage is rotated at 2 radian per second. So O2P is link number 2. It is rotated at 2 radian per second. 2 radian per second. You give the direction counterclockwise. Counterclockwise, as shown below. The angular velocity of the coupler we call it as 3. So we want to find out omega 3. Omega 2 is given, we want to find out omega 3. Try to locate I12, I13 and I23. So I12 is already located, I23 is already located, not I13 is not located, okay? Try to locate I13. How to locate I13? So draw a line passing through 1, 2 and 2, 3. 1, 2 and 2, 3. Draw a line passing through 1, 2 and 2, 3. Similarly, draw a line passing through 1, 4 and 3, 4. So 1, 4, 3, 4. So I13 lies here, okay? So the remaining eye centers it's not required to locate. So for these two links, if I write the angular velocity ratio theorem, so it's omega 2 into distance between I1 to 2, 3 is same as omega 3 into distance between I1, 3 and I2, 3. Okay. Omega 2 is given in the question. So what's the distance between I1 to 2, 3? I1 to 2, 3. What is the length of this link? O to P. Length of link O to P is A. This is A units. So omega 3 into distance between 1, 3 and 2, 3. 1, 3 is here and 2, 3 is here. What is the length of this link? O2, O4. This length is also A. This length is also A. The total distance is 2A. Okay, sorry. Omega 3 is 1 radian per second. What's the direction of rotation? Direction of rotation, this is the common eye center for 2 and 3. This is I12, this is I13. Both are lying in same side, both rotate in same direction. Try to answer this question. So he's asking us to do velocity analysis for the given configuration, okay? So he's asking us to do velocity analysis for the given configuration. So the given configuration is something like this. So this is fixed link, link number 1. This is link number 1. This is link number 2. This is link number 3. This is link number 4. Try to look at the instantaneous centers. So I12 will lie here. 2 and 3 are connected by turning pair. I23 will lie here. So I34 will lie here. So I14 will lie here. So I want to look at the remaining eye centers. So draw a line passing through these 2 points. So wherever these 2 lines intersect, that gives you I24. This is I24. And if you try to look at I13, you draw a line passing through these 2 and you draw a line passing through these 2. I13 lies at infinite, okay? So I13 lies at infinite. So I24 lies there. So the question is, for the 4-bar linkage shown in the figure, the angular velocity of link AB. So here angular velocity of link AB, that is angular velocity of link number 2. Angular velocity of link number 2 is given as 1 radian per second. So the length of CD is 1.5 times AB. CD is 1.5 times AB. So in the configuration shown, angular velocity of link CD is asking us to find the angular velocity of link CD, that is link number 4. So for this links, we can write angular velocity ratio theorem. Omega 2 is given in the question. He is asking us to find out omega 4. So angular velocity ratio theorem for these 2 links I am writing like this. So this is omega 2 into distance between, so I12, 24 should be same as omega 4 into distance between I14, 24. So omega 2 into the distance between I1 to 24 should be same as omega 4 into the distance between I14 and 24. So omega 2 is 1 radian per second, it's given in the question. So I want to find out omega 4. So to find out omega 4, you need to find the distance between these 2 eye centers. So I14 and 24. Or I am writing like this, omega 4 is, so I12, 24, so divided by I14, 24. Try to find out this distance. If you look at these 2 triangles, you can see here, if you look at this one, this is one triangle, and if you look at this one, this is another triangle. These 2 triangles are similar triangles, okay? They are sharing 2 common sides. So for the 2 triangles, these 2 sides are same, or I can say, so this angle is same for both the triangles, and this is 90 and this is 90. if two angles or two sides are coinciding, then these two are similar triangles, okay? For similar triangles, ratio of corresponding sides will be in proportion. Ratio of sides will be in proportion. So this is AB, this is CD. So I1 to I24, this is the base of the smaller triangle. Base for the smaller triangle is I1 to 24. And for the bigger one, the base is, so I1424. Should be same as the ratio of corresponding heights and the ratio of corresponding hypothesis. The ratio of corresponding heights is, for smaller triangle it's AB, for larger one it's CD. This is equal to the ratio of corresponding hypothesis, but that's not required. I'm writing like this. Omega 4 is I1 to 24 divided by I1 for 24. This is AB by CD. So in the question he gave this one. AB by CD is 1 by 1.5. Okay. So omega 4 is 2 by 3 radian per second. And it's clockwise or counterclockwise. This is counterclockwise. This is the common eye center. Both the eye centers are lying on the same side. This is also counterclockwise. You can go for polygon approach, you'll get the same thing. Which formula to explain? This is your angular velocity ratio theorem, okay? Angular velocity ratio theorem. So this is omega m. So whenever you write omega m here, it should be 1m, and the common eye center is omega m, mn. So this is omega m, this should be omega n. If this is omega n, it should be I1n, and for mn, the common eye center is Imn. So now you write omega 2, so I12. So you are doing velocity analysis for 2, 4, right? The common eye center is 2, 4. So this should be omega 4 and 1, 4, 2, 4. Okay, just listen here, everyone. This is the question that's given. This is the question, okay. So, in the mechanism given below, if the angular velocity of the eccentric circular disk is 1 radian per second, the angular velocity of the follower link for the instant shown in the figure is. He is asking us to find out angular velocity of the follower. He gave velocity of this particular disk, okay. Try to look at the instantaneous center. So, I am calling this is link number 1, fix a link. So, this is link number 2. The disk I am calling as link number 2, and the follower I am calling it as link number 3. There are 3 links. Here you can see link 1 and link 3 are connected by a turning pair. So I13 will lie here. I13 will lie here. So this is link number 1 and this is link number 2. So 1 and 2 are connected by a turning pair here. So I12 will lie here. This is link 1. So 1, 2 will lie here. I12 will lie here. So wherever 2 links are connected by a turning pair, so there the eye center lies. Okay. So they are in the same plane. So even though they are not in the same plane, if you know the distances, that's fine. We don't know the distances. So this is I13. 1 and 3 are connected by a turning pair here. So 1 and 2 are connected by a turning pair here. I12 will lie here. So he gave angular velocity of link number 2, eccentric circular disk. Omega 2 is given in the question. Omega 2 is given as 1 radian per second. He is asking us to find out omega 3. Angular velocity ratio theorem is like this: omega 2 into distance between I12 to 3. It should be same as So omega 3 into distance between I13 and I23. Okay. So if I want to solve this problem, I need to find the distances between I12 and I23, but I have not located I23, right? So I13 I have located, I12 I have located. I need to look at the common eye center for 2 and 3. How to look at the common eye center for 2 and 3? What kind of contact is there between 2 and 3? So what is 2 and 3? What's links 2 and 3? How links 2 and 3 are connected? So it's a point contact, okay? It's a disk. It's a disk, and this is a tangent to the disk at this point. So it's a point contact, it's a higher pair. So for a general higher pair, we have seen the instantaneous center of rotation lies somewhere around the common normal. So for a general higher pair, I center lies somewhere along the common normal. So this is tangent to this circular path, so this is normal, so it passes through the center, okay? Okay. So I center lies somewhere along the common normal, but where it lies, we exactly don't know this. But we have one more thing. So we have this Arenhold-Kendry's theorem. So whenever three links have relative motion among themselves, the three eye centers should be collinear, okay? If three links have relative motion among themselves, the three eye centers formed from them should be collinear. Here I have already located two eye centers. So I can say the third eye center should lie on line joining these two eye centers. The third eye center should lie on line joining these two eye centers, according to Arenhold-Kendry's theorem. According to Arenhold-Kendry's theorem, all the three eye centers should lie on the same line. And according to your higher pair concept, it should lie on this line. So I can say this is a common point for both the lines. The common eye center for links 2 and 3 will lie here. I23 will lie here. This is the location of I23. You give this distance is 45 mm, and this distance is 5 mm. Omega 2 is given in the question, this is 1 radian per second. Distance between 1, 2 and 2, 3, this is 5 units. So omega 3 we need to find out. Distance between 1, 3 and 2, 3. So 1, 3 and 2, 3, this is 50 units. Omega 3 is 0.1 radian per second. Whenever you come across any higher pair, for a higher pair, eye center lies somewhere along the common normal, okay? So polygon trick is not required here, okay? Here only 3 eye centers are there, right? So if you have more than 4, I can say 6 eye centers, so then it's difficult to locate. There we go for the polygon trick. If number of unknown eye centers are more. Okay, if there are only 3 eye centers, you draw a triangle, all the 3 lines are connected, right? What is there which is not connected? So it doesn't work here. Okay. It's very simple. So there are 3 bodies, and all the 3 bodies are having relative motion. As per Arenhold-Kendry's theorem, so the 3 eye centers should be collinear. And a higher pair concept, so eye center should lie somewhere around the common normal. That's the only thing. Okay. So I23 is something. So these two are connected by a higher pair. So for a higher pair, eye center lies somewhere around the normal. And these 3 links are having relative motion, so eye center should lie on the same line. Already we have plotted these 2 eye centers. So if I draw a line joining these 2 eye centers, the third eye center will lie somewhere on this line. So third eye center should lie on this line, and at the same time it should lie on this line. So this is the common point for both the lines. So I23 lies here. So whenever you are given only 3 links inside the mechanism, so whenever they give only just 3 links inside the mechanism, so try to locate with the help of Arenhold-Kendry's theorem, okay? So you cannot have any polygon method here. So go according to the theorem, okay? So normal cuts the center, okay? So this is circular disc, right? This is a circular disc. And this is a straight line. It's a tangent. And you are drawing the common normal here. So it's normal to the tangent, okay? So all normals to a circle will pass through the center, right? It's a kind of cam follower mechanism, okay? It's a cam follower mechanism. Try to solve this problem. Try to solve this problem. So I'm taking two pulleys. So this is a bearing. This is a bearing. So in this bearing I have this shaft. On this shaft I mounted this bearing. This pulley, okay. I mounted one pulley. So here I'm considering one more bearing. So on this shaft I am mounting one more pulley. Okay. So radius of this pulley I am assuming it is, let me say 2 meters, and radius of this pulley is 1 meter. They are big. So the distance between centers of rotations of these two pulleys is some 100 meters. So the distance between these two centers is some 100 meters. So I am connecting these two pulleys with the help of a cross belt, okay. You can connect any belt, so I am using a cross belt, right, for connecting these two pulleys. I'm using a cross belt drive for connecting these two pulleys. Let's take down this. Let's take down the question. So find the location of common instantaneous center for both the pulleys. Locate common instantaneous center for both the pulleys. So I discussed about this, what we say, a pure rolling motion, rolling with sliding, rolling with slipping. So what does that mean? And I clearly told you that, so in a higher pair the constant is only point of contact, okay. So kind of contact, based on kind of contact we are just defining that category as higher pair. Okay, and there is no restriction on what kind of motion we have. As long as we have point contact, it is a higher pair. Try to look at the common instantaneous center for these two pulleys, okay. And while solving this problem, so whenever you want to apply Aron-Holt-Kennedy's theorem, Aron-Holt-Kennedy's theorem, so it's applicable only for rigid bodies, okay. It's applicable only for rigid bodies. For flexible bodies, don't try to use Aron-Holt-Kennedy's theorem, okay. And we cannot locate I center for flexible bodies, okay. If the body is deforming, we cannot locate. So whatever analysis or whatever the discussion we had till now, it's only for rigid bodies, okay. It's only for rigid bodies. If it is a flexible body, so the body moves in different fashions, okay. If I take this portion of the belt, for this portion of the belt, it is rotating about this center, okay. For this portion of the belt, if you ask me where is the instantaneous center, this is the instantaneous center. So for this portion of the belt, it is sticking to the pulley, so this is the instantaneous center of rotation. Whereas this portion of the belt, this is moving along a straight line, yes or no? This will be moving along a straight line. If I draw velocity vectors and if I draw perpendiculars to the velocity vectors, they will be meeting at infinite in the direction perpendicular to this plane. And this portion of the belt is also moving in a straight line. If you try to look at I center, it will be lying at infinite in the direction perpendicular to this plane. So different portions of a flexible body will be having different I centers, okay? So we cannot locate a single I center for a flexible body. So whatever the discussion we had till now, it's only for rigid bodies. And the Aron-Holt-Kennedy's theorem, so that's also applicable only for rigid bodies, okay? So while solving this problem, don't consider this belt. That's the only clue. Okay. So you try to eliminate that belt and try to locate the instantaneous center of rotation for both the pulleys.